Hmm. I think we should get started. So welcome everyone to lecture 10 of CS 5.5, which is the introduction to robotics course. So last class, we covered the motion models and some sensor models, which we will be making use of in this lecture when we talk about localization and mapping, which are some of the very fundamental problems that robotics people try to solve and face very often. So just some logistical questions, or logistical things. So homework 2 is due February 13th. That would be tomorrow. And I see there's some discussion on Piazza. So, if you have a question, you can ask there, and we'll try to do our best to answer them. Or we also have the TAs also have office hours later this week if you want to use some late days for that. Lab 2 is due February 25th. So hopefully you've at least seen what it's asking you, and it will be asking you about some localization questions, which is partly the subject of today's lecture, although we're going to be covering some slightly different aspects of localization, but hopefully today will at least give you some help in terms of how to do the lab. So I think we'll be seeing some, if you look at the YouTube video, that a number of views, hopefully this one has another spike. Uh, yeah, and any logistical questions? I have the Google Doc open if you want to type in your question there, but yeah. Although usually people like to do that with the bigger the class is. Like the smaller it is, the more people get comfortable just raising their hand. Uh, yeah. Hmm. All right, so I think we should just dive into the technical details for today. All right, so we're going to cover localization. At least in the first half of today is going to be localization, and then we'll have mapping of the second half. So our focus today is going to be on mobile robot localization. And the problem statement is determine the pose of a robot relative to a given map of the environment. So if you remember from last class, we were thinking about that robot that was operating in a 2D plane, like maybe the floor. And then if the robot that had a translational motion, like translational velocity and angular velocity. So the translational one like makes it move forward, the angular one makes it rotate. And then by doing that, you can like basically move anywhere just by rotating some amount and then going straight. And we are going to assume that we are given a map of the environment. And so essentially what it means is all we have to do is only, and I say quote only because it's not always easy, but it's at least easy to describe. So you have basically we'd have to make sure that the map has some kind of global coordinate system, and then the robot has some kind of local coordinate system. It might be, usually there's some kind of center or a root joint of the robot where there's a coordinate frame centered at it, and then the origin is there somewhere. Yeah, so if you have like a mobile robot, it kind of makes sense that the center of it, if you look down from a top-down view, that's probably where the local coordinate system is centered at. And basically, we just have to figure out like where is that coordinate frame in the bigger global map. Yeah, and it again, it does assume an accurate map is available. If a map is not available, then wait until the second half of the course to think about it. But many times a map is available, right? I mean, if you go on Google Maps, you will often get a map of, most places where humans can go to in the world, and then you have your map, and then can, use it as part of your calculation. Same thing with many buildings and floor plans. So most buildings don't have construction going on all the time, so the floor plan is usually pretty stable. So, and then the challenges are that code is not usually sent directly. You have to infer it from data. So one way that, this book, the textbook that we're using, especially assumes that we have range sensors where we have a given robot. It's someplace then their wall, then it can fire a light beam at the wall, and then you measure the time it takes to return, you get a distance. And then if you do that multiple times, you can sort of form you can make an inference in terms of like where the robot is, right? Especially if you know the map, then it kind of becomes a little bit easier that way. But if you're just given one measurement, that would mean like one measurement of like one range finder. So it would tell you the distance of the robot to like one wall, right? But usually you'll need more of those measurements. Like if I look at, this wall, and then I have one beam sensor, I might know that I'm some distance away from this wall, but if I'm looking at a different wall, like I can easily have the same range sensor reading, even though I'm in different locations. So you need more than one measurement to infer the pose in, all but the most trivial types of problems. Yeah, so this is the sort of the overview of the localization problem. So let's talk about Bayes net. This is the prior Bayes net that we have all been using for the last few classes. So we have X here, which is the state of either the environment or the robot. So for this lecture, the state is going to be the robot pose for the most part. The U's here are the robot controls, so like the action that it takes, and then these are some kind of measurement, so like range finders, for example. And this is how the system evolves according to different time. So if we're trying to do localization, the main thing that's different is that we now have an observed map. And the reason why it's shaded is because we assume you're just given one. So if you're not given a map, then you would not shade that. So that gives you a sense of like what the mapping Bayes net will look like. But this is the localization one. So we're assuming we're given this map. And we also make the assumption that, the map is not changing over time, right? Like the map just has this M, so there's no MT. Which, I mean, usually that seems reasonable. I mean, most maps don't change too much. So we'll just have a fixed map that with the arrow that points to the different measurement. Yeah. Because when you have your sensor and then take a measurement, it's going to depend on what the map is. All right. So some different types of localization problems include, we have to consider local problem versus global problem. So position tracking is like if you assume the initial robot pose is known, whereas global localization means you just don't assume the pose is known. So you might have to assume like if the robot is in the map, so again, you're given the map, you might have to just assign uniform distribution to any possible location. Yeah. And then there's another variant of that, which is called the kidnap robot problem, where the robot can get teleported to different locations. So it seems kind of obvious that global localization is harder than position tracking, right? Because you're assuming strictly less information. Now, the kidnap robot problem, so most robots don't get kidnapped very often, but the argument here is that we care about the problem because in practice, many localization algorithms have some failures. So it basically measures, can your localization algorithm recover if, if all the time you thought the robot was somewhere, but it turned out you got some new measurement and that highly suggests that the robot is in a completely different location. So again, it's kind of silly how we assume robots can get teleported. The real motivation here is to be robust to failure. So that's the motivation here. So again, this is like a taxonomy of different problems. So you'll want to consider that when you think about your own localization problem and the assumption that you're making. And then there's static versus dynamic environment. So with static environment, the only thing that changes is the robot pose, and dynamic means things can change. So clearly dynamic is harder than static, and dynamic one might mean maybe a humans or moving obstacles that cause a lot of changes to the sensor reading that we use to try to figure out where is the robot. And then there's passive versus active. So passive localization means, well, the robot is moving, but it's not like actually trying to learn more about where it is. Like it might be moving from something else, or someone else might be controlling the robot to do a completely different thing, like, move as far as they can. And then the localization just says, the robot is moving independently of any localization objective, figure out where is the robot. And then active localization means you actively try to move the robot to learn more about where it is. So there's another distinction there. And the fourth and maybe final type of localization problem would be if you're considering a single robot versus a multi-robot localization problem. Yeah. And this is an example of a type of localization problem that you might get, like if you're looking at the textbook, this is one of the figures that they have, and we're assuming that you have some kind of mobile robot. So again, if a mobile robot, it moves in a 2D plane. This is like your top-down view of what the map looks like. And when environments are symmetric, like that's when it gets harder to localize, right? Because if the environment is completely asymmetric, then if you measure some stuff, you can kind of get a sense of where is the robot. But if there's two like rooms that are completely identical, and then you're measuring stuff, then you basically boil down your localization to assuming, well, I'm in this position in one of the rooms that in one of the symmetric rooms, but we don't know which one it is until you do something to get out of that symmetry. Yeah. So that's why for something like this, like if you let's say the robot is like this robot is like facing to the left, this one is facing to the right. So both of them see that there's a wall in front of them by like maybe 1 meter. I'm just making up some numbers, but you get the idea here, right? Like robot is facing one direction, you get one measurement, and then the issue with this is a perfectly valid belief given that measurement, but this is also another valid belief. Yeah. But if the robot goes in like this room, then there's something like this anywhere else, so you can break the symmetry and then learn more about where the robot is. So what we're going to do today is talk about how can we use the extended common filter to help with localization. So for now, we're talking about EKF localization, and then in the second half of class, we'll talk about EKF SLAM, which is simultaneous localization and mapping. So that already kind of gives you a sense of like what simultaneous localization and mapping mean, but here we're just doing localization where we have the map. Yeah. And so we have this example where the robot is along some kind of hallway. And the point of the Kalman filter is to derive a belief over where the robot is. Now, the belief can be specified with just one value because it's some X value along this line, right? So because it's like one distance value, then you can argue maybe Kalman filters are okay because we assume we assume Gaussian when we work with Kalman filters, and if you have a single distance, then maybe the true distance is like has a single mode with a small amount of Gaussian noise. So yeah, so for a lot of like, tracking, then I think people like Kalman filters for that. Yeah. So another thing that you might want to be aware of is that we're going to assume that the existence of landmarks in the map, right? So the landmarks are, you can think of them as like fixed points throughout the map that indicate, things that the robot can use to understand where it is, right? So in real life, a landmark could be, this famous building or the location of the street or location of your favorite statue or something like that. And they're just like different things on the map that if a sensor detects it, then you can use that to have greater confidence about where the robot is. So in this example, the landmarks here are going to be the doors, right? And I think we showed this example in the lecture about Kalman filters, but the main thing that's different is that we're assuming that correspondences are known. And that just means that if we measure a landmark or we detect something, we know what it is. In practice, maybe you might not know what it is. So that adds another degree of difficulty. So we're going to save that for something else, maybe. So for today, we'll assume correspondences are known. So we assume that the robot is facing this door, you know, this is door one. Yeah. So if it wasn't known, you would have to come up with new random variables that describe, your distribution of what you think this door is. So. Yeah, and then in this example, what's going on here is, so A here, this is like the initial belief of the robot pose. So this is position tracking, which is the easiest type of localization. You just assume, okay, here is the position of the robot. We know it's positioned with some amount of Gaussian noise, right? And then whenever the robot moves to the right, but before incorporating the measurement, then that will cause the belief of where it is to shift, but also with increased variance. That's why this Gaussian has a slightly fatter distribution because it has higher variance compared to this one. Because B is trying to show this is what happened before you incorporate the measurement. And the measurement is what? Like, what's the measurement here? Yeah, so the measurement is just, the robot looks at the door and then it knows, well, it looks at the wall and it knows like where in the wall it's looking at, basically. And if it sees that there's a door in front of it, it knows exactly what door it is. Because we're assuming known correspondence. Then basically that's what's going on. You see, like the robot now takes into account the measurement model, which is probability of z given x. Then it convolves that with the prior belief to get the updated belief, right? Yeah. So everyone sees like why this Gaussian has a smaller variance than the one up here, right? Yeah. Because when you take a measurement, you improve the knowledge of where the agent is, so you can use that extra knowledge. So this is a common like pattern in Kalman filters. Every time you make a measurement, your Gaussian should get sort of a narrower. Same thing applies in 2D. Like if you have 2D and you have the iso contour that visualize the covariance, it should get smaller if the measurement give you enough update about where the robot is. So, all right. All right. Yeah. Question?
We're giving features or like identify features.
So I think your question is, what is given in the map? Is it like the full geometry information? Is it all the correspondences? And it's like, you're asking basically what is given in the map, right? The answer is it depends on the problem domain. So for localization, you should just think of the map as giving you all the complete information that I guess you would need for the robot to know where it is, assuming you have a good like localization algorithm. So the exact choice of a map is, it just has to be something that intuitively just gives you enough information. It might be geometry information, it might be other types of information. Maybe it also includes like text information about the description of like what the rooms are and so on. But there's no fixed, there's no more precise definition than what I can just describe to you. So there's a lot of customization here. Yeah.
So if we can just give maybe the number of the doors. So if we just go back to the slide 7, the symmetric problem, we can just identify these two possible positions by comparing the maybe the door numbers. It's right. So maybe just give a number of the doors.
All right, so I think you're asking like we can maybe it's not a local maximum. Yep, the map includes more information about like the doors, or maybe if it also includes like indicators of which wall the agent is looking at. Like if there's extra information here that says this is wall number 7, then this is wall number 42, then it means this is no longer a local maximum, right? Because you can distinguish which one it is. If you have that, then sure. So, but again, I think the door numbering is mainly because these are kind of like special things that, but again, the design of a map is like largely up to whoever designed it. So. Oh yeah, so last class, you might recall that we talked about a motion model, the velocity motion model. And remember the problem setup, like you have again a single like mobile robot operating on a 2D plane. Like this is the plane, this bold circle is the robot. And remember that, remember what were the controls here? There's 2 of them, 2 components to it. So yeah, there was the translational control and then the angular control, right? So the translational one means, well, you have to define a direction where the robot is facing, right? But if it's facing this direction, which is kind of suggested by the way the diagram is made, then no angular velocity, but only translational one. Translational one means the robot just goes in this direction. And if you have angular velocity, it will rotate. So if it rotates and it moves in a direction, it can reach like anywhere in a 2D plane. And this was the velocity motion model that we derived last class, where this is the robot pose like at time t-1. And then this is the robot pose at time t, right? So this whole thing is a state. So if you remember the BaseNet, it would be like the xt term. Except it's a little bit confusing because there's already an x component here. So that's why like we don't indicate it with x, we just show like the full vector. Yeah. Yeah, so you have the prior pose, then the next pose. Again, if you're comfortable with the T being here, then you can put it there, but just understand that it just means this does not refer to the X coordinate of the robot, but like the full state. Yeah. And the controls are specified as UT with the two numbers that specify, translational and angular velocity. So again, the whole point of this was to show, given the current pose plus robot action, what is the next pose? Again, if you're not dealing with this type of mobile robot, if you're dealing with a different type of control, you'll have to change this model, right? But under the assumption that we have a 2D robot, a robot operating in 2D with control, those two things, then this is the motion model. So at this point, let's have our objective be to review, like, what does it mean to use EKF for localizing this robot? Under the assumption that we have that dynamics model from the last slide. Also assuming that, again, assuming the known correspondences, so if we measure something and then we measure the distance to a landmark, we know what the landmark is. And we're also, I'm going to explain this a little more later. We'll assume that we have sensors that return some feature. So the features might themselves be, like distance or other values. So yeah, whenever you see like feature-based, just think of this as, features are just like some statistics or other things that could describe whatever we care about. They could be like, I mean, these days they're often like learned as the result of machine learning, but I guess, in the old days when the book was published, you could hand design, features for things. Yeah, the book was published in 2006, I think. So before you were born. So this algorithm, the localization will be derived from the standard EKF. So remember what the EKF was. It was trying to represent beliefs as multivariate Gaussian. So the input is your prior Gaussian, the control, and the measurement. And then G is the nonlinear term that we use because it's extended Kalman filter, so we don't assume an exact like linear model here. That's what the G means. And same thing for the H. Yeah. So they're nonlinear functions. So we'll have to use the Taylor series, the approximation to linearize them. So if you want to compare like what the different inputs are like, so this is your standard EKF. I think you've been working on that for your homeworks too. The EKF for localization assumes this input. So you see that a lot of this is the same input, but what's changed, right? CT and M. Yeah. What's M? What's M here? Yeah, the map here, right? So, and then CT is the, oh, well, I guess I kind of gave it away here. The map. Well, a set of features, you should think of a set of features as being part of the measurement here. So a set of features is like part of V here. And then the corresponding variables are CT, right? So don't spend too much time thinking about what the correspondence variables mean. They're just like integers that tell you this landmark corresponds to this thing. If you don't assume known correspondences, then like this wouldn't be part of the input. You would have to come up with some model that gives you like a probability distribution over what we think each landmark is. But let's try to keep it simple for now. So this is the input. All right. So when we try to do EKF for localization, we'll start with like analyzing like, what is this G function and how do we linearize it? So again, the whole point of EKF is to find the updated belief by linearizing the motion and the measurement model. So first we'll linearize the motion model, and then we'll linearize the measurement model. So if you look at the derivation, actually, what the book does is it divides the motion model into two parts. Like this is like a noise-free part, and then there's a noise part. And again, this is a motion model because this is our robot state at time t-1. This thing is something that depends on the action that you, and then you combine this with the noise to get the next state. That's what a motion model is here, or a dynamics model if you call it that way. And again, this is still using the same velocity motion model that we covered last class. And so what happens here is to derive what, so I think what we're trying to do is derive what a GT means. So remember that when we linearize in extended Kalman filters, we linearize it like this. So this is the true function that we're trying to linearize. We linearize it by considering what is its value centered at mu t-1. So really the linearization is about the mu t-1. Like the ut is just an extra input because you need to know that for defining the function correctly. And then gt is the Jacobian. And the rest of this is just like, you're writing out what a Taylor theory means. So if you look at this line here, what we want to do here is to get what is G, right? So I think I'm gonna spend a little bit of time looking at this because like I think the confusing thing here is like the notation, so we should try to make it a little bit clear here. So the point of this is to try to define like what is the Jacobian, because we need that in order to like actually use the EKF. And this is the standard way to define the Jacobian when we are linearizing the function g. And we differentiate it with respect to xt-1. But what ends up happening is we differentiate it, and then when you write out the Jacobian definition, you get something like this. So the way to think about this here is that the output vector is this thing, right? It's a three-dimensional output. And so when you have the Jacobian from a function, which is defined from a function from, some vector to another vector, then each row means you consider the same component in the output. So that's why you have x prime at the top row, and then the middle row you have y prime, and then the bottom row you have theta prime. Yeah. And when you differentiate with this term, what this is doing is it's just denoting which component of the of this we're considering, right? So normally when you write out the definition of the Jacobian, it looks something like this, right? Let me write it out. Yeah. So you have the Jacobian when you're considering functions that are vector values. So they go from one vector to another. And usually when we write out the Jacobian, for the first time to make it clear like how it's defined, then we'll use like f of x, where you have f of, x1 to xn equals, f1 to fn. Yeah. So this is how I try to visualize what this formula is trying to show. So I start from this. This is the type of function that we consider when we're reasoning about Jacobian. The input is some vector, the output is some other vector. In our case, again, the output is this thing here, right? And so this output it plays the role of this thing here. And so F1 is just like the first component, and then Fm is like the last component of it. And this is what the x prime and y prime and theta prime mean. They're just like different components of the output. Yeah. And then you can look at the formula for a Jacobian and then just apply that here. So that's how I try to reason about this. So I hope that helps. And this is, if you do the math, this is what results. If you want, I can go through the math and do some examples of different components of this. Like when you do Jacobians, usually working through one of the components in the output, it helps you to do all the others because you just use the same pattern for them. I'm going to do one of them anyway. Just yeah. Well, what's the question? Sorry. No, the Jacobian is not always a square matrix. So the Jacobian, so I removed it, but if you have f of r and to r m, so if it's like this, the Jacobian would be, I'll double check out the way, but it's over the x1. Yeah. Um, yeah, so this would be if m rows in m column. So it's not, it doesn't have to be square. Yeah. The Hessian is a different type of matrix, and like different matrices in like linear algebra, like they have to be square, but the Jacobian doesn't have to. Yeah. In fact, I think we showed in the extended Kalman filter lecture like an example of a 1/3 Jacobian. I think I showed that in class. And by the way, just see how this works. So F1 is the output, like the m-dimensional output. That's all the x prime, y prime, and theta prime, and the x1 through xn. They're the different components of like what is input. So that's the new t-1 here. That's why it goes from x, y, theta, x, y, theta, x, y, theta here. Do you want to do one of the calculations for GT? Yeah.
Could you please just use this story item on the first line to give us example?
So you mean like maybe this component, like the top right?
Yeah.
Okay, let's do that. Let's do that. Now, I don't have much room here, so I'm going to try to, yeah. Yeah. All right, and this is, okay, this is D x prime over D. All right. What is x prime? Well, First, let's write out x prime. Uh, is that clear? So it's just the first line above, right? All right. Now, what this is happening is you're differentiating with respect to something, right? So we're differentiating with respect to theta. So the reason is we have the Jacobian is defined on like the input is defined on like mu t minus one. So when you have mu t minus one as the input, you get theta as like you get like what this term is. So it's basically the theta component of that. So this reduces to d over d theta. So because this theta is just a particular value of mu t minus one that was like that's the input to here. So yeah. So all right. So what happens here is you just differentiate it with respect to each of these components. So this goes to 0, you get minus e. Actually, let's move this out here. So what is the derivative of sine of theta with respect to theta? Remember? What is okay, then so what happens is they essentially replace theta with like mu t minus one theta, which is the theta corresponding to that vector. So again, I think the notation makes it a little bit more confusing, but it's kind of hard to like write out the notation anyway. So I think this is the best we can probably do. This is the top right component of the Jacobian. So yeah, hopefully that helps. Yeah.
Why, why do you consider about the noise? And zero RT on the previous slide, we just ignore it or?
Oh, so you mean the RT? Like what happened to the what? How do we deal with the RT?
Noise actually.
Yeah, that's RT. That's this thing here. Because what we're doing here for the derivation is the book makes the split between this is the noiseless part and this is the noisy part. So I only showed like how to do the noiseless part. And then we assume there's some noise here. And how to deal with that precisely, I decided not to cover it because there's already too much to cover here, I feel like. So if you want to see the details, you can look at the book and then they show how to include like how to find the necessary Jacobian for that too. But I felt that would be a little bit too complicated for the lecture. And yeah, so hopefully if you if we've done the top right, hopefully the other components are not, or like at most the same difficulty. Yeah, again, usually when I work with Jacobian, doing one of the components is enough for me to know how to do the other. Yeah. All right. So that is how we get a Jacobian. And the next thing to take into account is the measurement. Oh, do you want a picture of the map? I was blocking the photo. Do you want to take it? Yeah, but I was blocking it when you were taking it. Yeah. All right, so let's talk about the measurement, right? So the measurement is going to be based on, again, the assumption of what we mean, like what is our measurement model basically? So our measurement model has these features on it. So these are like 3 features for each measurement. We have RT, BT, and FT. And then I indicate the index in the measurement vector. So when a robot uses a sensor to get a vector Z, the ZT of the measurement, it'll look like this, but you have ZT. You have a bunch of the different measurements. Each of these is like one particular landmark or a point location in the map. And then each of these additionally has 3 numbers, which are these things here. So how do we get the numbers in here? Well, let me just cover that right now. So the measurement vector consists of a collection of these triples. Now let's look at how one of them is computed. So this is how to mathematically derive like what is the thing that you just saw on the last slide. So this is our circular robot is somewhere on a 2D plane. S is like some, some signal about the measurement, so about the landmark, right? So the landmark is this big black circle. R is like the range, and then like C is the bearing. So R is, like the distance from the center of the robot to the landmark. And the landmark has coordinates mx and my. Now, if you're considering multiple landmarks, then you have to assign like another index to say, this is the index of that measurement. So that's why you get so many indices. It's kind of frustrating when you look at the equation. Yeah. So this is what happens. So just think of the MJX as just MX, right? So if it helps, just ignore the J because you're assuming that maybe there's only one landmark, and then you can drop the J. If you have multiple landmarks, then of course you need that index to distinguish between them. Yeah. And again, the way we're going to get the sensors are for the range, we're going to assume that we compute the distance from the center of the robot to the landmark. And this formula here is just the definition of Euclidean distance in 2D. Right. So that's what happens here. The angle, like the angle that we're talking about with the bearing, like that, that's this angle here. So that's the phi here. And this angle is going to be the arctan 2 of these 2 components minus theta. You see how to get that? Yeah. Yeah, again, I can do some very quick sketch. Yeah, so the angle, I'm assuming there's a perpendicular angle here. So because of that, then this angle is phi plus theta, because theta is this part here. And when you have the tangent, then the tangent of this is equal to, well, I basically wrote it there. It's M1. So because this is the distance from like this subtracted this and like the difference between this and the y coordinate here. So that's like the distance. Then there's another distance from mx to x, and then you apply the arctan2 to both sides. So if you look on like if you look at the definition of arctan, it helps to take care of different cases of which angle you might be at in the coordinate system. So yeah, I think if you look at what a tan 2 mean and like numpy or other code, you'll see that it covers like this is basically what it means here. Yeah. Yeah.
So the a tan two right here is just a different equation of the arctangent function in mathematically different for the number.
So you're asking more about like what is the a tan 2? Yeah, so the a tan 2 is, yeah, it is a way of like mathematically writing out what is the arctan of this fraction. So I don't want to go into too much of the detail, but you can look at like on I think NumPy has an arctan2 function, and then you can look at the documentation of what that means. Yeah. Yeah. And then when you apply the arctan2 to both sides, you get phi plus theta. So you subtract theta, then that's why you get this last term. And then finally, S is some signature, so it may be a numerical value about that sensor. Yeah. And then we finally apply zero mean Gaussian noise to each of the components. Yeah, so if you're looking at the book and you're wondering like why this equation is like this, then it's basically because of what we just derived. And these are the three different features for a given sensor or given landmark. Now, you might argue, well, why are we using just these features? We should have more features. Then if that's the case, you should add more things for your own feature sensor model. But for simplicity, we just have these three features. Yeah. I mean, I think these days you would maybe use a machine learning model that would just automatically generate like a lot of interesting features automatically for you. But yeah, then so we're doing something similar again here. We put in we have the measurement model here, right? So the measurement model is given the pose of the robot, what is the probability of a measurement? So the pose of a robot is xt, right? So xt is the position and the angle of the robot. That is input here, then you get the output. So again, so yeah, you remember that like p of vt given xt, that's the whole point of the measurement model. And this is what we have here. So what happened next? Yeah, so linearize and evaluate the Jacobian, sure. Uh, so whenever we do this, it'll look like this. So we have the function here. It is approximately equal to that same function, but we change the input so that it's at the mean value. Now, again, the notation here of J and M, that's because we assume that this is extra information is there, but the main input that matters is the X here. And then this is the predicted mean. And HTI is the Jacobian, where it's specific for that feature. And then you do that for all the features you might have. Again, normally you don't do this algebraically, you have your code run it, but just to make sure you have done it before, we'll go through the math. That's generally how things work in computer science anyway. So this is how you compute the Jacobian. So this Jacobian is equal to the partial derivative of this xt. So this xt is a three-dimensional vector. The output is another three-dimensional vector because the ti is a 3D vector, and so the Jacobian is 3 by 3 because the input and the output are both 3 dimension. And again, it's done in a similar way as before, where each row you apply the partial derivative on the same output. So RTI, this thing here is the first row of the Jacobian, and then that is the output that we take the partial derivatives are for each of the columns. So that's why you have RTI of the first row, BTI of the second row, and STI as the third row. And then this is what you get. Yeah. Anyway, let me go through one of them anyway. I'll go through one of the components, and then hopefully the other will be a bit clearer. Which component do you want me to do? I can do one of the ones that gives you 0, but it might not be educational, because usually if you have a 0, that means you did d over d x of something that didn't depend on x. I can do one of these components.
Maybe first and second.
First and second, what do you mean by that? First row, second column? All right. Here's, all right. So, let me, all right. That makes sense. And partial derivative of this thing, which is what this really means is if the derivative with respect to this y, which happens to be the y that is inside mu t bar at this time. This is just plugging in, what's in the top row. All right. Now you do this, and then you get well, all right. Well, first, the 1/2 goes here, then you get -1/2, so it turns into the denominator. So you get 1/2 times. Yeah, so you can see why there's the square root of q there. Yeah. This is the chain rule. So you got the partial derivative with respect to y of this thing, which doesn't depend on y. When you go here, the 2 goes down, and then the 2 goes down, and then you have just the y here. So 2, 2, and 2. And then yeah, -1. So because that's the chain rule of the negative y. Yeah. So this is 0, then this is the result of taking that partial on this term. And then what the way that they write it is we assume that this x is the value of the x that is part of this vector. So that's why they have the mu t x bar here and also there. Oh, and then you have the 1/2 and the 2 that cancel out. That's huge. Oh. Yeah, so this -1 I'm pulling over here. Yeah, I think that's it. Yeah. That's all I'm going to do now. I think doing more will take a lot of time. So, and again, if you've done one of them, usually it becomes clear how to do the other. Anyone want to take photos of this? Yeah. It's like 4 people taking photos. Huh. All right, so if we have to summarize what we did, what we have done so far is we have done EKF and we have determined what are the values of the G and H matrices, which are the Jacobian that happen when we linearize the motion and the measurement model. And if you, this is the extended common filter, and then this is the same thing, but when you localize it. So again, don't try to look at every line. Again, don't try to look at every line here. Just you can look at table 7.2 if you want more information. I think part of the reason why it looks long is because they set some intermediate values, like you have Q equals this, so that you can write out the vector, then the Jacobian, then a little bit easier. But I think the bigger takeaway is to know like roughly what each step is trying to do instead of like going through the calculation too much. Yeah, so again, we skipped some detail about this, but we did cover like how do you compute the G vector here, the G matrix here? How do you compute like the mu here, which is the motion model, and then you have the measurement model here, that's the HTI, right? And there's a for loop over different features, right? So this for loop is iterating over different landmarks that might have been detected in the current measurement vector. And then at the very end, we get the updated value of mu t and the covariances. Yeah. And then yeah, I think P is like some kind of distribution over the different features. All right. Do you have any questions about this? Let's just give another example here. So if you imagine that you have the landmark detection sensor where you might have like a more accurate sensor in the top row and the bottom row has a less accurate sensor where we also assume that the dashed line is an estimated robot path from the motion model while the solid line is the actual path. So I think the dashed line and the solid line, they are the same with the two rows. So the only difference is how good the sensor model is. And the way to interpret that is if you look at the iso contours of the multivariate Gaussian, then they're basically bigger for the less certain or the noisier sensor, right? Because if it's noisier, then there's more sensor uncertainty. And so the variance must be bigger. So you have less precision about where the landmark is located. So I think the bigger takeaway here is just to be comfortable with like reading what these plots mean. Like if we show, what happened, what is going on when the uncertainty becomes from the lightly shaded region to the dark shaded region, you should be able to say things like, oh, it happened because of a measurement. So to quickly recap, so we covered EKF localization, assuming known correspondences where the different landmarks, which are just points in the environment, or in the real world, they could be things like this statue, this building, this garden, or something. We did make other assumptions. We did assume a particular choice of the velocity motion model and the feature-based sensor. So for a different problem, you might have to change the computation of the matrices that we just talked about. So when correspondences are not known, then you typically have to do something like, you try to estimate what the correspondence variables mean, and then you pick which one is most likely for a given landmark. So if we don't know what a landmark is, then include another variable that is the distribution over them. And then, yeah, there's another algorithm in TBF, the textbooks. I think it's even longer than the one that we just covered. So you can look into that in your own time. I think that's a good time to take a 5-minute break, and then we'll cover mapping right now, right after the break. Have a good break then. We'll be back in maybe 5 minutes.
this one. This.
By the way, I should say, I have not been able to look at the homework, but I actually haven't really looked at homework. So I think if you have a question on that, I'm better to ask on the team. If you back on mine, I can also, if back on the piazza, I think we will get to your question, but I haven't yet, but I haven't actually looked at this one. Okay, yeah. Right, about one more minute. All right, so let's get back to some of the content here. So in the first half, or really the first like 60% of today's lecture, we covered the localization problem. So now we're going to talk about mapping. So we previously assumed that the robot had some kind of map in advance. So we just gave it some kind of map. But in some cases, we don't have a map. And then that's what the mapping problem means. You just have to construct the map. And the challenges are that, well, there's a huge hypothesis space. So it depends on how exactly you define a map, but no matter what, a map is like some high dimensional array of numbers, right? And then like you have to decide like the full design of the map and so on. So there's a huge hypothesis space. And the other main challenge is that you might also have to learn localization as well. So you might have to localize the robot to know where it is. Because if you know where the robot is, then it helps when you're making the map. Because otherwise you might be making the map, but if you don't know where the robot is, it gets a little bit tricky how to do that. Yeah, so I think it's called a chicken and egg problem. So what came first, the chicken or the egg? I'm not sure. So this is a mapping example that's from the textbook. So if you imagine that this is like this to the left is like your data from the range sensor. So whenever the robot is at some location and then it shoots out a beam from the range sensor, you'll get some kind of black dot. And then you combine all those together, you get stuff that looks like this. I think what's going on is like they overlay a bunch of different data when the robot is at different orientation. So like maybe from the robot's local frame, it looks like there's a whole bunch of different hallways there, but it's because the orientations aren't aligned between different readings. So I think that's what's going on in the figure that they made. And the reconstructed map should look something like this. So yeah, a bunch of raw data, then ideally the reconstructed map. And you can kind of see how this can be challenging. Hi. So remember the base net that we had when we were talking about localization. So it's like the same base net that we have been covering throughout the semester up until today, where we introduced this M, which is an observed map. So what is our base net now for mapping? What does it look like? I'll give you another 10 seconds to think about it. And if you're looking at the slide, please don't look ahead. It's part of the mental exercise to try to think about this during the lecture. But if you've already downloaded the slide, then that's also fine if you want to use it to learn before. So what's happening here is, again, I kind of made a trick assumption, like I wasn't clear like what we were assuming or not. So if we assume that we know the robot poses, then our base net could look like this, and we don't even need the control view. I mean, why is that? Because if you know the two poses, then that gives us all the information we need to know about. If we know the exact xt minus 1, then we know what it leads to for vt minus 1 at an xt. And if you condition on this, then you don't need anything else in the conditioning by the structure of the base net. And the whole point of mapping if we make this assumption is that the map is probability of M given all the sensor reading and all of the true state. Or the known robot poses, at least for this lecture, because we're assuming that state is the same as the robot pose. Even though like the state could also include like environment features, which we will actually get to later. So what happened now? So based on the wording of simultaneous localization and mapping, well, what do you think the base net should look like? So now it's not just mapping, it's simultaneous localization and mapping. So what becomes unobserved? Yeah, the Google Doc has been quiet, not just today, but the last few classes too. I don't know. It's mostly when the number of people here is much larger. All right. So you see what happened now? Now the x's do not become observed. They become stuff that we have to make inferences on or learn a distribution of. I mean, I think that's much more realistic. And here we don't know what M is. So this is the whole point of what simultaneous localization and mapping mean. We have to figure out what is our robot state and what is the map. I mean, yeah, the diagram is a bit misleading. If you shade in xt, it becomes probability of xt and M given the other information here. Of course, yeah, if it's xt plus 1 is the same thing. Like, it's basically the same except you change the t to t plus 1. Yeah, yeah. So this is online SLAM. So we're trying to find the updated information about both the map and the next pose. So what about the full SLAM problem? Okay. Yeah, so if you're doing the full SLAM, then you have to figure out like what are all of the poses here. So you have the probability of x1 to t and M given v1 to t and u1 to t. Yeah. All right, does this BaseNet make sense for everyone? Again, it's just a model for describing how the system evolves over time, and the unobserved variables are the things that we are trying to like get some distribution about. So let's give some example videos. Yeah, so this is an example video of doing some kind of slam with a mobile robot. So here's a mobile robot. So it could be like the robot that operate in a 2D plane, like all the ones that we have been studied so far, that we have been studying. Yeah, so you can see that these people are used to robots because otherwise they would be taking pictures with their phone, right? So yeah. It's gotta be either a conference or like some warehouse where, oh, except that guy. Yeah, that guy, I don't know what the child is doing. He's like taking them, yeah. But if you look at what's going on in the top right, that's trying to visualize what is the SLAM doing. It's giving you both the map as you construct it, then I don't think they explicitly visualize like what is the distribution of the robot, but like I think the circle is, if the center of the circle is like the highest probability point of where the robot might be. And then maybe they're assuming that the variance is stays the same or something. So yeah, this is completely staged because these guys would be looking at the robot. Yeah. But it's a really nice video though. Yeah. And then yeah, I think what they do is they end up showing how the robot can move, and then I'm gonna skip ahead a bit. And with something like with SLAM, and then with the map that's constructed from it, then you can make the robot go to certain targets. And then you get you get stuff like that. Yeah, so you see it needs a 2D plane, so that's why it can't go above the step there. So you can also do SLAM not when the robot is operating just on the floor, but also in the air. So this is an example of aerial navigation. So yeah, the first author is very, and also actually all the authors, they're pretty good at like aerial like robots. So they're the robot here. I think this is the UPenn campus where you just set the drone, and then this visualization is showing like the map. Uh, and I think what's going on here is, they're also visualizing like the best estimate of where the robot is located, which is the localization problem. Yeah, so I think if you're doing stuff like SLAM with this type of robot, you need to use a different type of motion model because it's operating in, I think, in 3D now. So you have to use different controls than what we were using for that planar robot operating in 2D. But the same like technique is applicable roughly. Just have to change and swap the different matrices and motion and measurement model there. Yeah, then you get a nice, what they end up doing is they get a nice 3D map of the external environment and then the building that we're in. All right. So it's like with localization, there's a form of using extended Kalman filters for localization, you can also do extended Kalman filters for SLAM. And again, the approximation and assumption that the model makes are that, at least that we're making here, that we're using, again, feature-based maps which have point landmarks. So it's the same as the EKF localization. You assume that 2D robot, of that robot operating in 2D, where it has a rangefinder that can measure some features corresponding to a single point, which is a landmark. And then you have a bunch of landmarks in your environment. We do make Gaussian noise assumption for motion and perception. Why? Because it's extended Kalman filter. The whole point of using Kalman filters is to rely on Gaussian assumption. So if we don't rely on those, then we should not use EKF. Yeah. Then I can't process negative information from the absence of landmark. So here's a little bit of intuition. There are 8 distinct landmarks here. You have 1, 2, 3, 4, 5, 6, 7, and 8. If we observe a landmark, then the intent is that, if you observe a landmark, it should improve the knowledge of where the robot's position is. Because if I see that this landmark, the statue that I know is somewhere, and I see it, then I should have a reasonable idea of like where I am just by deducing, the distance from me to the statue or something. So the nice thing here is that if you assume like where's one landmark, the intent is that it should also help with improving the estimate of the other landmark. So what happens here is the robot is operating in some trajectory. The robot operates this dashed line. So in A, the robot has moved and then has seen 3 landmarks. So it hasn't seen the 4th, the 5th, the 6th, the 7th, and then the 8th. So it's only seen the first 3. Now, as the robot is moving, its uncertainty increases. Because we don't assume we know the exact robot position, because that would just be a mapping if we did that. But we're doing simultaneous localization and mapping, so you need to know both the location, but we need to get a distribution over both location and the map. Now, the interesting thing that happened with going from A to B to C is that the robot is going in this dashed line curve. And each time it moves, it'll measure the sensor that is like closest to it, and the noise keeps increasing. That's why you see the ellipses that are getting bigger. But when the robot moves and then it sees this landmark that it has already seen before, then that suddenly reduces the uncertainty of all of the landmarks. This is essentially what a good SLAM algorithm should be able to give you. Because if we see a landmark again, then we have a better sense of like where we were. Like if I'm in a maze and I don't know where I am, like maybe, I get dropped in a maze for some reason, and then I try to navigate out and I remember a bunch of landmarks. And if I see one again, then I know, oh, I have a better idea of where I was in all the prior landmarks that I was at. Yeah. Yeah, so that's why all the transparent, or that's why at least all the ellipses corresponding to the landmark, they just shrunk a lot. The only reason why the pose doesn't shrink is because this is like online SLAM, so we only care about the probability of like the next pose. Yeah, then because if you remember all all 8 of these landmarks, they're embedded in that map variable M. So M is like this map that has all of these landmarks together. And that's the thing that we determine at every time step, but the robot pose, we are only doing it for one pose at the upcoming time step. So it's not like all the poses. So we're going to, again, derive the EKF SLAM algorithm. We're going to go a little bit quicker this time because we don't have too much time to cover it, but just to give you the basics of how it roughly works. So this is the state vector that we're going to consider. Remember that in SLAM, we're now trying to determine the robot state and also the map. Because if it was just mapping, then we wouldn't need the XT. We would condition on it and assume it's given. But now we're just going to assume that our state is XT and M, where robot coordinates and landmarks and signatures. Any questions about this state representation? Yeah. So what is the meaning of the signature? What's the meaning of the signature?
Yeah, so it just, the way we mark the landmarks, right? We recognize landmarks.
Well, yeah, the signature is just a way to identify the landmark in some sense. So like, imagine the landmark gives you a single color signal, and different landmarks give you different color signal. Then, yeah, this is just the book's shorthand for saying like this is some numerical value that identifies this landmark. And in addition to its position. Yeah. So the whole point of EKF SLAM is to calculate this online posterior. Yeah. So remember that this is what I think I was mentioning in earlier classes that the definition of a state is like kind of ambiguous. So the state so far has been usually this is the pose of the robot. But here you can argue that, well, the state here consists of the robot and the environment. The environment is like this landmark and stuff, this landmark stuff. Because this is the thing that we're trying to estimate. Because otherwise, when we were doing localization, we were automatically given M. So this is, again, just a way to design like what is the vector that we want some kind of distribution over. And because there's a lot of components here, like it intuitively it becomes a bit of a difficult problem, which kind of makes sense because you're doing both localization and mapping. All right. So the algorithm for EKF SLAM is kind of like EKF localization. So you have you first have a few lines that apply the motion update, and then you have lines that incorporate the measurement. So again, it's like EKF localization. You have this stuff incorporates the motion, given the robot, estimated pose plus the action. What is the next pose? That's what the motion model means. Then you incorporate the measurement. So, given the robot pose, you have the measurement. Those are the Z vectors. How do we use them to update the next, mean and covariances of the robot position, as well as like the next update of the map too. Yeah. So we're gonna go through some relatively quick derivation where we do assume that there's known correspondences. So if you can see it, I'm not sure how clear it is to see, but the input includes the C, right? So the C is the correspondence variable. we assume that they're known, so if we look at a landmark, we know what it is. Yeah. And again, it's a recursive algorithm. You have the mean, the covariance, the U, and then the Z, like the measurement. So a quick question. So no, this is like what the input is, but where's the map? Where's the map here? So the map is part of mu, right? So remember that now we have this. So the map is part of y. So if we get mu, then mu is now going to be the mean of both the robot pose and the variables that describe the map. Yeah. So if you're wondering why there's no like m term, it's because it's inside the mu, right? It's inside there. Yeah, it's a question.
Is that like an augmented rotation?
Yeah, it's like augmented state in some sense. Yeah. Yeah. So when you, all right, if you try to initialize it, then what is this doing? Mu of 0 is like your initial estimate of both the robot pose and the map. So remember that mu and sigma, they now contain both the robot pose and the map information. Before, if we were just doing localization, you didn't need the map there because you were given it. But now we have to include it here. So what's happening here is we're just assuming like all zeros. Is that a good assumption? I mean, do you have any better idea? I mean, if we don't know where any of the landmarks are, then like I'm not really sure what numbers to put there. So 0 is like maybe it's as good as I can do. Why are there infinities here? Like why is this infinity here? I mean, in practice, if you write it in your code, you would just replace infinity with like a large number. Maybe it's like np dot inf. Like what does this mean here? What does this mean? So if you remember, so this is like our state. So mu is going to be the mean of the robot coordinate and the landmark. So if you do the covariance has to be of dimension 3n plus 3 by 3n plus 3. So this part of the covariance, the bottom right, that's all the landmark stuff. And if we don't assume anything about them, then we kind of have to have like an infinite variance. If you try to model like where they're located with a Gaussian, but we don't know anything about where they are, then you might as well just crank up the variance. And because we just don't know where the landmarks are. Again, if you have a better estimate, like if you're working on a robotics problem where you have some estimate, you should probably put that in there. It's going to be better than this. Yeah. All right. So again, we're assuming that the robot is operating in a 2D plane with the same motion model that we were talking about for the localization. And that's reflected here. Like if you look at this term, it's similar to what we had earlier and also in the last class. And Y here is that thing that has both the pose in the first 3 components, and then it's 0 for all the others. Yeah, why? Because this is mainly the motion model is only affecting where the next pose of the robot, but the landmarks don't move. So it's like we don't have any further changes of that from the motion model. You do get changes when you like measure that's different. Yeah, so what happens here is the state vector is like the first three, then you have a whole bunch of zeros that just serve to indicate, where are all the remaining components that correspond to the map. Yeah. Everyone see why this is zero? Like, because again, the first three rows, they're the result of applying the robot's action. But if the robot moved, then we're assuming it doesn't move the landmark. Again, you might argue, well, maybe you should model that. If that's the case, then I would recommend you add in some more terms here. But I think there's already enough here that you don't want to add more. And for notational reasons, what the book does here is you simplify this to this type of matrix algebra. So if you go from this here to the bottom, then it's the same thing. Like this thing is equivalent. You just have fx, which is the matrix of size 3 rows and 3n plus 3 columns. And then you transpose this so that this thing is 3n plus 3 by 3. And then this thing is 3 by 1. And so the matrix algebra works out, and then you get a 3n plus 3 vector. Yeah. Yeah, so again, this is mainly to try to make the notation a bit more easy to manage. So this is what happened in line 3 here. Yeah. Yeah. So again, the whole point up here is to get them kind of posterior over y, where y is the robot pose and the landmark. Yeah. So again, this part will update the robot pose, the measurement will update the landmark. Yeah. And then essentially what happened again here, and I'm not going to go through the details, but you again rewrite this in terms of, here is the noiseless part, here the noise part, and then what happened? It's EKF. What happened? Yeah, so the motion function is approximated by the first order Taylor expansion where you have G. So remember that the motion model is now UT and they're the YT minus 1, right? Because Y is like the state now. And I'm not going to go through the arithmetic. You can just see what it looks like. And then you get like this G term here. All right, very quickly, how do we incorporate the measurement? So for the measurement, we're again assuming that we follow that same rangefinder where you try to find information about a landmark with the position to it along with the range and the signal. And this should look familiar because it's basically what we covered earlier in class. So yeah, remember why this is? Like I had it over. Oh yeah, this might be, it starts over here. None of you asked me to do any more math. So no. Huh. Yeah. So again, we're assuming the same measurement model. So again, I'm not going to go through with the detail because we've already covered it, but again, just assume that we have the same robot. We're trying to measure information about this landmark, and then based on this, we get more information, really like 3 features for a given landmark. And then we have a collection of them and then use them to update the robot's estimate of of the map too. Yeah. And then, once again, we are here, then you linearize and compute the Jacobian. I'm not going to go through the math, but it's basically what happened here. So remember that this is like really modeling probability of the given X. So then X include the action and then the map information, because this also has the map here, like it has M terms here. Oh. Yeah, so again, trying to wrap up this algorithm. So with EKF SLAM, I think basically most of the updates are very similar to the EKF localization, except you have to make your matrices much fatter or much taller in order to accommodate the extra map information. Yeah. So that's why it can be a good exercise to go through, but I think the more important thing is to really understand, like what is really going on here, like the higher level depth of what each line means, and So if you want to, I would recommend you can go through the map on your own. I would recommend doing the localization first, because then you can assume the map is given, and then here you assume that the map is not given. So, all right. Any questions about this? All right. So quick summary. So today we covered localization and mapping. So localization, try to find the robot pose. Mapping, try to find the map. Simultaneous localization and mapping, you have to do both. And yeah, SLAM is a very, very fundamental problem in many robotics tasks. So it's kind of important to know it. And then, yeah, moving up. So for next week, we'll be switching gears to some more like broadly applicable topics, including, oh, sorry, then next Wednesday, sorry, not next week. So Wednesday, we'll be covering the math programming. And then next week, remember, we don't have class next Monday, but it's next Wednesday, we'll cover configuration basically. Yeah, I'll see you on Wednesday then. Bye.